Now that you know how to navigate within the Verity viewer, we're going to finish out part 4 of the training by going through the QA/QC tools and process, making sure you know how to review the analysis results by item and to make any adjustments or corrections needed. Outside of the view and navigation tools, the primary tools you'll need for the QA/QC process are down here at the bottom of the toolbar. And we'll be going through those as we go through a mock QA/QC process on this data set. To get started, I'm going to sort these items by their item description from Navisworks, and then we're going to go through them one by one. Now, we've gone through and picked items out of this data set that have a lot of different failure points, just so that we can demonstrate the conditions where the algorithms aren't going to be perfect and will require a little bit of user intervention. That's also a great way to teach you the different intervention tools and make sure you remember them. So do bear that in mind. Generally speaking, this algorithm is going to operate between 80% and 95% correctly on most types of data. But again, we're going to look at a lot of the fringe scenarios in this data set. To get started, we're going to take a look at this condition where our algorithm has misclassified the installation status of an object. I'm going to go and turn on the auto zoom up here in our host connection tools, and what this is going to do is cause Navisworks to zoom in on an item once it is selected in Verity. Now this works about as well as the clash detection auto zoom feature does, which means sometimes it will place you with a wall in between you and the thing you want to look at. In those cases, we have an inspection mode you can check as well, which will turn everything transparent except for the item that you're looking at. I'm going to leave that off for this point in time so you can see other items around these. Now I'm going to go ahead and minimize Navisworks and maximize Verity so we can see the impacts of this, but keep in mind that if you have this on two screens or split screen, you'll be able to see what's in Verity and what's in Navisworks at the same time. So to resolve this, all we need to do is come in here and modify the installation status. And in this case, what we have is a return sidewall grill, but instead, you and I can probably see there's something round sticking out past this ductwork. And that's actually flex duct because they decided to put the grill elsewhere and never updated the model. So I'm going to note this as being not found because there was no actual grill there. The algorithm couldn't know that because there is no flex duct model, of course, and there is a flat object at the end of these points, which is why it fit this flat grill to that flat set of points on either side of the ductwork. Now at this point, I'm going to go ahead and deal with the review status. So having looked at it, feeling confident in the final result, I'm going to click this little checkbox here. This is going to give us the opportunity to type in an approver name or initials. I'm going to type mine in. If you want to track this, you can. Otherwise, you can leave it blank or skip it and just change the review status directly. But if you check that box, it will change both the review status to reviewed and put the reviewer in here. So it's a real quick way to get both fields. And then we're basically going to go through the rest of these elements in a similar fashion. This one here we have flagged as occluded, and the reason why is because the actual installed grill has this shape to it with some different fins in it, and that is not anything like the shape that was modeled. So here our algorithm sees there are points that it doesn't have a good fit on that are between the object and the scanner, and for our algorithm that means it's occluded. Now, you and I know that this was just not modeled accurately, so again, we can go through here, change it to installed. The software will then show us the best fit that it found, and since the object and the points are not really a good match, this is the kind of condition where a fitting algorithm is not going to be highly successful. So we can go in and make adjustments. Now, as I move this, you'll notice that all the numbers are changing and updating. So if I move this into place and rotate it, moving can be done with left click and drag on the as-built object, rotating with shift left click and drag. If I move it and rotate it into place, I'll get accurate observables. And this is going to give me a pretty good idea of where this is located relative to the points. It would be great if what was modeled and what was scanned were the same, and we'd have an algorithmic optimized fit, but this is more than good enough for the kind of data that you're going to need for this type of scope of work. And I'm going to turn on a heat map now. Look at our as-built heat map, and I'm going to regenerate it. And so when you move an object manually, we're going to let you finish moving it before recalculating the heat map, because that step can take a couple seconds. That way you're going to end up with a pretty fluid experience moving it around. Click that button, we have an updated heat map, all of our numbers are correct, and so now I can say that this one is reviewed as well. Now here we've got one that's flagged as uncertain. And uncertain is our way of saying that there are a couple different places we could fit this to. The data is not really conclusive as far as our algorithm is concerned. And you can see here between this pipe and the end of the grill structure, it found some points, and then it also probably found the actual location, or at least close to it. So this is again the opportunity for the human to intervene and say, we know exactly where this was installed. It was back here. And that looks pretty good. Again, I can recalculate that heat map and move on to the next one. And this last one is another condition with our wonderful flex duct extension, so I'm going to move this to not found. Now, we have keyboard shortcuts for most of these tools. You can find them in the user manual, but I'm not going to be using them today because you can't see my keyboard, and that would make it pretty hard to figure out what I was doing. But keep that in mind, because that does make it quite a bit quicker when you're working through a bunch of items to review. Moving on to the next item, we have another condition where what is scanned and what is modeled aren't really a good match. So in this case, we have a piece of ductwork that only has the sheet metal modeled, and what was scanned is actually the insulation wrap around it. So this object is basically 2 inches larger on every side than what's in the model, and that object is not really of a consistent thickness. It's going to get tighter at the corners. So again, this is a condition where algorithms are not going to be able to find the right result, except in extremely rare situations where you have equal density on the sides, top and bottom, in which case it'll do pretty well. But that doesn't happen very often in the scanning world. So this is going to be something you're going to need to adjust. And we have a couple tools we haven't talked about yet to do that. The first one to note is the reset fit. So in this case, we've found a bit of a rotation here in more than one direction. That's going to be hard to kind of back down. So you can click this button and it will move the object back to the designed location. At that point, you can pretty easily move it into place, at least what you feel like is close to into the place. And you can see we've got a pretty big transverse shift here, so we'll pull that back. And at this point, we're probably pretty close. So I'm going to, again, recalculate the heat map, and we can take a look. Heat maps are useful for things like this because if we've done a good job, we should see a pretty similar distribution of colors on all the different sides where the object's visible. And we know on the bottom it's going to sag a little bit. It's about 2 inches thick. And here we've got a 2-inch tolerance, and that means our heat map is going to go from green to red, and red is going to really be that 2-inch mark. So maybe we shifted a little too high here, so we can pull it down a bit. Recalculate as many times as you want, and that's probably a pretty good fit. I'm going to approve that and move on to the next one. Do the same thing here. Refit. This one is pretty tough. So I feel like this is probably a relatively good fit, but we have very little data on this item. And so while I could call this installed and accept it, I'm more comfortable with saying that this one was just occluded. Again, that means that we didn't have enough data from the scanner. It was blocked by other items, and that's a good way to handle conditions like this rather than, stating that you're sure about a number when you don't really have a lot of points to make a determination. Again, duct wrap. So I'm going to pull this up. Looks pretty good vertically. recalculate, move on. Now you'll notice I got distracted and forgot to approve a couple of these items as we were talking. You can approve multiple items at the same time, so I'm going to go back here, look at my straight duct that I had forgotten to approve, use the Shift select modifier to select multiple items, and then switch those on to approved. So you can certainly go through and do this multiple items at a time if you prefer. And with that, we are pretty much through the ductwork on this project. And so that's pretty quick to go through. Obviously, it takes a little bit longer when you're talking people through things. You can go through items usually 5 to 10 items per minute, sometimes up to 20, particularly when you're getting a lot of good fits. And you'll probably see that as we get through some of these other scopes of work, because they tend to be a lot easier for the algorithm than something like ductwork with duct wrap on it. Now there are a couple of other conditions that can be challenging, and so this is another good example where we have just points that are around the object that imply, in this case, a circle in the point data, and the object is circular. And our algorithm weights how close you are to something, generally making the assumption that if there are two things that look like the object, the one that's closer to it is the one that it represents, which most of the time is correct. But in cases like this, where the metal deck and the unistrut and the stirrup make a bit of a circle, it's not going to get the best result. However, in this case, the model data and the scan data are very similar. So unlike the others where you have to be pretty precise, drag it into a location because that's going to be your final measurement, here you can just get it pretty close and hit the refit button. And that refit button is going to use the same algorithms that we use to fit the geometry automatically, but based on your user input, so that it picks the location that you pick. And so now you can see we've got a very good fit there, and we can move on to some of the next items. So this pipe here is pretty much white, matte, and so it scans really well. So you'll see for the most part on this mechanical piping that it's been very easy for our algorithm to find the right location, barring some of the conditions like that last one. So this is a good fit. Here we've got that same pipe where we're very close to the deck and we're picking up that circle from above, so drag that down, hit refit, and now we've got a good fit. Can approve it, and then now we're into pretty much all of these are going to fit very well. So again, this is where that shortcut key can really speed things up for you. And then here's another one where we've got just a little bit of cutoff on the scan data because of another object, and it makes it a little hard to find the right location and rotation for that elbow. So again, I'm going to reset that fit, move this over, move it down a little bit, and hit refit. And again, that refit will take your rotation and location into place a little bit more strongly. So we'll approve, and we're through our mechanical piping. This is fire sprinkler, and this is another condition where the material is not ideal for scanning. So this is black pipe, it's matte, so it doesn't reflect very well. But in this case, we have really good fits because we've got pretty good coverage, and we don't have insulation that's around it that's causing a discrepancy between the geometry and the scan data. So you'll see here again that we actually do quite a good job with this sprinkler pipe. This one didn't really have enough data to be particularly conclusive. It was about a ½ inch pipe, and we've decimated the points. But you'll see if we switch this from occluded to installed, that it did find the right fit. It just wasn't a strong enough fit for us to feel confident. And generally speaking, our algorithm is going to err on the side of telling you something is missing or out of tolerance or wrong, as opposed to telling you something that's actually wrong is right. So we try and pick those conditions whenever possible and lean to that side just to be careful. Some more fits here. And back into some mechanical piping. And here we have a condition that if I open up Navisworks, you'll see that this pipe is actually not installed in this location at all. It's probably about 6 feet away. They decided to install it very differently, and this is actually where it crosses over itself running the opposite direction, these 2 points right here. So this the algorithm is classified as not found, and that's probably the correct selection. Now, in this case, we've got a bit of a challenge again. So here, the modeled pipe and the installed pipe are actually a different radius. Now in this case, this is the correct one. Knowing this project, they ended up changing the sizing in the field, and it works just fine. But this is one of those conditions where our software can't detect that something is the wrong size for you. But as you're going through the data, it's very easy to notice these discrepancies, and that can clue you into something that you might need to look into, look at the drawings or make a few phone calls to figure out what's going on. I should also point out that racks of pipes can be a bit of a challenge. You could pretty easily see a scenario where this pipe, its as designed location, would be closer to the installed location of a different pipe. And if that were the scenario, we would very likely fit this to this location over here. Again, that's where the refit tool and the manual move comes in handy. You can, of course, move it to a different location and fit it to those points instead. And that's where looking back and forth between Verity and Navisworks, with Navisworks as the contextual viewer, is particularly relevant. Let's take a look at some walls. In this case, we have another condition where we have misclassified the object. We've said this is occluded, and you can see by the points there is a wall there. But when we only have a very small portion of the object covered, cases like this, we may flag it as occluded because we're not really confident about the fit we can get with such a small portion. And also, is this part of the wall installed or this part of the wall installed? It's just, again, us being a little bit careful on these things. So I can change this to installed. And you'll see part of the reason why we want to flag these things. So it looks like this wall maybe is not such a good fit. If I change the opacity of my as designed down a little bit, and same with my as built, so they're not affecting the colors as much on the heat map, you can see it's a pretty even gradation. And if we get in here and look at it, you'll see that our fit is not actually very good. And that's because there's a bunch of different things on the surface of this wall. There aren't a lot of points, and since we don't have the whole thing covered, it's pretty easy to get rotational errors on these kind of things. So this is why we flag them with something like occluded or uncertain, so that you have the opportunity to go in and look at it and manually intercede and fit the wall. In this case, the wall was installed pretty straight. It just was installed a little bit off where it should have been. So make a couple adjustments here, recalculate my heat map, and you'll see now we have a really good fit. At this point, we can improve it, move on to the next wall, and you'll see these we have a lot better coverage on. And so again, when I say that you really want to have good coverage, on your items, the better your coverage is and more even the distribution, the better the algorithm's going to do with fitting things. So when you're scanning for use in Verity, you definitely want to optimize your scanning in the field with that in mind, with lower resolution scans, but more scan positions. That's going to give you better results. And here we found an interesting case where a wall that was supposed to be installed was not actually installed at all. So this was correctly flagged as not found. Last, let's take a look at some structural items. So here you can see a column. In this case, of course, the plan view is going to look like you're looking down the object. And you'll see we've got good coverage on 3 sides. The points are pretty well spread out. So again, a very easy fit for us to make. We can approve that. Let's take a look at a beam here. Now we've got sparse data, but it's scattered along the length of the beam, so we've got good coverage, and so that really gives us everything we need to make a pretty good fit. So we can approve this one and move on. Now here, this one is flagged as occluded, and you can see there really is very little data on the beam. So again, this is a point where you can make a judgment call. Do you want to leave this one as occluded, or do you want to make an adjustment? We can pretty clearly see that, over here, there is data. So if we switch to installed, it'll give us its best fit, which is not very good. And we can go in here and drag it into place against this data. Now this probably isn't a good idea for a job that has a lot of requirements on accuracy. But if we're just trying to get a rough idea, we can see this one is pretty far out of place on this end of the beam, at least, where you have points. So I can recalculate my heat map and move on to the next one. And here we've got plenty of good data to fit. We've got a pretty good fit, and this one's very close to where it should be. So we can pass that, move on to the next one. Move on to the next one. And here we see a beam that's actually pretty far out of vertical alignment, just in terms of being at a pretty steep angle. But it does look like we've fitted a little bit high here in terms of the data. So I'm going to pull this back down, and then based off that input, I'm going to tell it to refit. Let it take another longer pass at this particular one. And we've got a little bit better fit now, so that looks pretty good. And here, even with, again, pretty sparse data, we're able to get a pretty good fit on this because, again, the coverage, we've got points all over the beam and on both sides of it. Another fit. Another good fit. And then this one is another one of these cases where we have data only on one end of the beam. The data on the end here is pretty far away. Most likely this beam probably bows a little bit in the middle and then comes back at the end. That tends to be pretty typical for steel. But in this case, since we don't have data at that end, we're just showing the beam at a pretty sharp angle compared to the original. But I'm going to go ahead and approve this, and at this point we're done with that QA process and pretty much ready for reporting. So we will be moving on to part 5 of our training. Thank you for bearing with me through that. I know it's the longest of our training videos, but if you think about it, we spent about 23 minutes going through 50 different items and have fully QC'd them. And just think about how long it would take you to do that in the field to this level of detail. So definitely a big efficiency improvement. And yeah, let's move on to reporting.